The main point of this video is to introduce you to using expected value calculations and show you how you might use these calculations to evaluate different policy alternatives. We're going to be interested in situations where there's uncertainty about what might occur. Let's start by defining some terms. First, expected values are calculated by taking the value of a particular event and weighting it by the likelihood that it occurs. We'll see this more in practice, and hopefully that will make more sense. Probability is the likelihood of a given event occurring. And finally, risk is the probability of an unwanted event. In order to get us started, go ahead and pause the video and answer the question on the screen. How much would you be willing to play for the following game? When you're ready, come back, press play, and we'll talk about it. The expected value of this game is equal to $3. How do you get that? Well, you multiply the two outcomes, the value of those outcomes, times the probability of seeing them, and add those up. So there's a 50% chance you'll get $5. So 5 times 0.5 equals $2.50. And then there's a 50% chance you get $1. 1 times 50%, or 0.5, gives you 50 cents. Now you add those together, you get $3. Now notice, you actually never get paid $3. You either get paid $5 or $1. But if you play the game a lot of times, in expectation, you should expect to get about $3 on average for every time you play. Now if you said, hey, I'll play that game for $3, that means you're risk neutral. But you might have said, well, I'll play and I'm willing to pay $4 to play. In that case, you're risk acceptant. Finally, maybe you said, I'll play, but only if I pay $2, in which case you're risk averse. So notice, the question was how much are you willing to pay, and that depends on your level of risk aversion. For most of the calculations we're going to do in this class, we're going to focus on giving advice based on being risk neutral. So how do we calculate expected values? Well, first, we identify all of the potential outcomes. We then estimate the value of each of those outcomes. We then assign probabilities, which give us how likely those outcomes are to occur. And then we multiply the value times the estimated probabilities. We add all of those up to get the expected value. We're going to do several practice problems to help drive this home. For the first practice problem, let's think about a situation where a local government is deciding whether or not to build a dam. They have these three options. Go ahead and pause the video and calculate the expected value for each of the options. When you're ready, go ahead and press play and I'll show you the answers. The expected value of option A is negative $60 million. There's no uncertainty. You pay the price up front and you know exactly what it will cost, $60 million. For option B, we start with the $15 million that you spend up front. You subtract from that the $800 million multiplied by 10%, or 0.1. We're multiplying it by 0.1 because we only pay the $800 million if the dam fails, and there's a 10% chance of that. The expected value is then negative $95 million. For option C, we pay nothing up front, but if the dam fails, we have to pay $800 million, and there's a 20% chance that that will occur. To calculate the expected value, we multiply $800 million by 0.2 to give us $160 million. Of these three options, option A has the lowest expected cost, so a risk-neutral policymaker should choose option A. I want to turn now to another example. In this case, the government is deciding how to deal with radioactive waste. There are three options, each with different initial construction cost, as well as different costs should it fail. And as you'll see here, we have both the expected cost and the probabilities of failure. Go ahead and pause the video and do your best to calculate the expected value of all three options. And when you're ready, press play and we'll go over the answers. The augured hole option has an expected value of negative 29. The other two options both have an expected value of negative 26. In all three cases, we take the initial cost, we add to it the cost that we have to pay if there's a failure multiplied by the probability of that failure. Here are the expected value calculations for all three options. Although the augured hole option has the lowest initial cost, it has the highest expected cost. This is because if there's a failure, which is relatively likely, it will be expensive to clean it up. The expected value of the other two options is the same. Therefore, a risk-neutral policymaker will be indifferent between these two options. Which option you choose depends on whether you want to pay more upfront and have a lower risk later, or if you want to pay less but risk paying more later. For our final example, we want to think about what a town should do about an old bridge. If it fails, it's going to cost $5 million to repair, as well as lead to lost fees. Here's the full problem. Go ahead and pause the video and take some time to try to calculate the expected value for both options. When you're ready, press play and we'll go over the answers. If they choose not to repair, then they pay $0 upfront, but there's a 5% chance they'll lose $7 million later between the repairs and the lost fees. So we simply multiply 7 by 0.05 to get negative $0.35 million. To calculate the expected value of repairing the bridge, you start with the $2 million they pay upfront. You then subtract from that $7 million times the probability of failure, which in this case is 0.01. Altogether, that brings us to $2.07 million. In this case, the risk-neutral policymaker should choose to not repair the bridge because that has a lower expected cost. That's it for this video. Keep asking questions, keep studying, and keep safe.